Hello, pre-calculus students. I am going to talk about the Chapter 5 test review or closure. I'm going to go over the problems. So for these first ones, we are given expressions in logarithmic form. So I am going to rewrite them in exponential form. So if it is an ln, a natural log, that means the base is e. So I'm going to rethink of this as e to what power equals this e squared, the fifth root of e squared. So it would be helpful if I had this written as a power instead of a root. And remember, anything to the 1/n power is the same as the nth root. So this fifth root, I can rethink of as the 1/5 power. And then power to a power, I multiply. So this would be, I multiply across the top and the bottom, e to the 2/5. And so this must be 2/5, right? This power must be 2/5. All right, this one I'm thinking 3 to what power is 1/3. If I want this 3 to move to the bottom, I must have a negative exponent. So this would just be -1, right? 3 to the -1 means 1/3 to the first, or just 1/3. Right here, 5 to what power is 625. So using a power sheet, not our calculator, that would be 4. 5 to the 4th is 625. All right, for D, thinking 2 to what power is 0? And there is nothing. I can't take 2 to any power to get it to equal 0. It's just impossible. So there is no solution. Remember, you can't take the log of anything 0 or anything negative. It just isn't possible. All right, here, again, the base is e if it's a natural log. So e to the 7th equals my question mark. And that's all I can do. My answer is just e to the 7th. All right, so this one, 5 to the 1/2 power equals what? And that's it. I would write it probably as a square root of 5, right? Going back to this idea of having a fractional power being a root, that's the same as the square root of 5. All right, for this one, I would have 4 to what power equals 16 to the 5th. It'd be helpful if these bases were the same. So I can rewrite 16 as 4 to the 2nd and then to the 5th. Power to a power, I multiply. So this would be 4 to the 10th. So then this must be 10. All right, here, now this is what to the -4th power is 16 over 625. So you can kind of puzzle this out in your head. You might think in your head, oh, I know 2 to the 4th is 16 and 5 to the 4th is 625. So, but then it's flipped. So then it would have to be flipped to be 5/2 instead of 2/5. The other thing you could do is just kind of algebraically think, if I want to get rid of this negative 4th power, then I'm going to have to take the -1/4 power of both sides, right? Because if I multiply those, it would be 1. And so then this would be 16 over 25 to the -1/4, right? The negative, that's just like having it to the -1st to the 1/4. So that -1 is just going to flip it. And the 1/4 is the same as the 4th root. And the 4th root of 625 is 5. And the 5th root, I'm sorry, the 4th root, the 4th root of 625 is 5. And the 4th root of 16 is 2. So 5/2. All right, this one, there's no base written. That means the base is 10. So 10 to the 5th is what we're looking for, which is 100,000, right? 5 zeros. Okay, so moving on to these equations, we're asked to solve without using a scientific calculator. So I'm going to start like this one. I'm going to rewrite it in exponential form. So 2 to the 6th equals x to the 3rd. 2 to the 6th is 64 equals x to the 3rd. And so then I can think in my head what to the 3rd is 64, or you could think of it as taking the cube root of 64, which would be 4. Okay, this one, I'm going to have to use my log properties to condense this before I can use my exponent properties, before I can rewrite it in exponential form. So if it's a log of two things being added with the same base, I can rewrite it as a single product. Right, so that becomes log base 4 of 3x, and then I'm going to rewrite this in exponential form. So at 4 to the 2nd equals 3x. So that's 16 equals 3x, and then if I divide both sides by 3, I get 16/3. Okay, same logic with this one. The base is now 5, so I have log base 5 of, again, two things being added. I can rewrite it as single addition. And then I'm going to rewrite in exponential form. So 5 to the second equals 3x. I'm going to divide both sides by 3. So x is 25 thirds. Right, this one, again, I'm going to condense. These are being subtracted. So this is going to be written as a single quotient, right? Two things being divided. And now this one is a little different from the first few because I've got a log base 3 here and a log base 3 here. So I don't need to rewrite it in exponential form. If these two sides are equal, that means these two expressions must be equal, right? They both have a log base 3 of something. Those two somethings have to equal each other. And so then I'm going to solve this equation. I don't like this divided by x here, so I'm going to multiply both sides by x. So I have 5x plus 2 equals 7x. And then I'm going to subtract this 5x over, and I'm going to have 2 equals 2x. And when I divide both sides by 2, I get that x is. And then this one, I do have a single log over here. I'm going to go ahead and rewrite it in exponential form. I know that looks kind of gross, but power to a power I multiply. So 3 to the 5x squared. It would be helpful if these both had the same base, right? Because I could take the log base 3 of this side, and I could do that here, take the log base 3 and get it that way. Or I could just rethink of that as 3 to the third. And so then I would have 5x to the second equals 3. I would divide both sides by 5. So x squared equals 3/5. And then we take the square root of both sides. So x could be positive or negative. And then, so it's the square root of 3/5. So that's like having the square root of 3 over the square root of 5. And then if I didn't want to have a square root in the bottom, I would multiply the top and the bottom by the square root of 5. So that'd be plus or minus, this would be the square root of 15 over 5. Okay. And again, the other thing you could have done right here is you could have taken the log base 3 of both sides, or maybe better yet here, because log base 3 of 3 to any power, that'd just be 5x squared, and then same thing here, like, or even here, right? Log base 3 of 27, you know, was 3, so you could get it that way as well. All right, so graphing logarithms. So there's more than one way to graph logarithms. The way I graph logarithms is I start with just a table for the parent function without any transformation. Like I know this +1 is going to move it up 1, but I just start with a table for the parent function without any shift or stretch or anything. So that would just be the log base 4 of x. And then I start with a table. And when I make my table, instead of putting in bases of x, which is kind of a pain because I have to think in my head, 4 to what power is this number, I start with my y values. And I always just start with -1, 0, and 1. Every time I start with the same ones. And so then in my head to get my x, I'm thinking 4 to the -1 power equals my x. So this is 1/4. Okay, for this one, I'm thinking 4 to the 0 equals x. So that's 1. And then here I'm thinking 4 to the first equals x. So that's 4. So that's my parent function without any sort of transformation on it. And you can do this a couple different ways. One thing you could do is you could just plot this parent function. So I could plot the 1/4 -1 and the 1, 0 and the 4, 1. So I could plot those 4 or 3 points and kind of do a sketch, right? And then I could take those 3 points and then I could shift them all up 1 to get my kind of final graph. So I could take this up 1. I could take, to change colors here, I could take this up 1. I could take this up 1. I could take this up 1. And then here's my graph. Right, so that's one way that you could get your graph. The other thing that you could do, and this is kind of how I usually do it, but really either works. Let me just kind of erase this. So here we go. Okay, I think, okay, my whole graph moved up basically 1. It's a shift up of 1. So I kind of do a dashed line there. That's my shift of 1. And then just based off of my new kind of X and Y axis, so now based off of like this and this, then I plot my points that are in my table. So based off of this, Then I would plot the point 1/4 from here, -1. I switched my pen. So that would be here. And then I could do 1, 0, and then 4, 1. So I get the same graph looking at it either way. Okay, so if I were doing this one, it's a base of 2. And again, it's got that 3 there. It means it's going to be a vertical stretch of 3, like an amplitude change kind of. But when I make my table, I'm only going to make my table for the log base 2 of x. And I'm going to start the same way with picking the y values, -1, 0, and 1. And I'm going to think to get my x, 2 to the -1 is 1/2. 2 to the 0 is 1. 2 to the first is 2. Okay, so I could plot those 3 points again, like I could do 1/2 -1, 1, 0, 2, 1. There's my kind of my parent graph. And then I could take those 3 and then triple my y values. So I could say, all right, well, this was at a -1. Now it comes down to -3. That's a y value of 0, it stays. That's a y value of 1, it comes up to 3. And then you can see your stretch. Whoops, not very good graph, but you can sort of see it. Right, or you could say, okay, all these y values here have to get multiplied by 3. So this becomes -3, 0, and 3. And then you could just plot those points. Either way would work. All right, this one, I know this causes a shift right 1. So for these, for me, I just would kind of put in, all right, a shift right of 1. It's like my y-axis is moved to the right 1. And I would make a table again for that log base 3 of just x. And I would make my table again where I pick my y values, -1, 0, and 1. And I think, okay, 3 to the negative first, that's 1/3. 3 to the 0 is 1. 3 to the first is 3. And you could plot those points and then move them all to the right. But what I do, like I did on this one up here, is just kind of thinking of it off of my translated axis. Now I plot the points. So from here, not from the 0, but from where I shifted, 1/3 and then down 1. And then 1, 0, and then 3, 1. Okay, and you can see when you look at the whole graph, it's that logarithm, but it's been shifted to the right. Okay, and again, you could have first graphed this just as is, and then moved every x value to the right. Right, so all of these would go to the right. So you could even think of it as adding 1, adding 1, adding 1, and then plotting that table. All right, this one we have another horizontal shift. This one is to the left, 2. Okay, and in fact, for this one, I'll do it kind of the other way, where I'm going to start with the parent function, which we already did a table for the log base 2 of x up here, right? So I would start with that parent function, log base 2 of x. I'm just going to rewrite the table that we had from the previous problem. And you could do it where you plot these points. So 1/2, 1, 1, 0, 2, 1. Right, so that was this here. That's like my parent function. Everything, though, has to go left 2. So that means I would take these 3 points and they would go to the left 2. Right? This would go to the left 2. This would go to the left 2. I really still do, though, like to draw in the asymptote, like the fact that this is moved to the left 2. It's just going to help me when I graph my function to make sure that I don't cross that where that an asymptote is. Right, so I do recommend drawing that even if you're going to do it differently. All right, I'm going to stop this video here and I will pick up with the second half another time.